In this video, we'll take a quick look at how to make a channel power measurement on a pulsed RF signal. Adding the channel power display isn't going to give you an accurate result because it's not synchronized to the pulse itself. Even if we used a max-hold trace, we're really just relying on luck and time to build up the spectrum trace of the signal itself. So we really need to synchronize on the pulse. In order to do this, we'll open the time overview display, which shows me amplitude versus time of the RF signal. We can see we're free running here, so the pulses are just walking through here randomly. So let's set up a simple power trigger. Bring up the trigger menu, trigger on the RF power when it crosses through, in this case, minus 26 dBm, and we'll turn the trigger on. And now I can see the leading edge of my modulated pulse. To ensure we make an accurate measurement of the entire pulse, we're going to increase the analysis length so that we look at the entire duration of the pulse itself. And by doing that, we can now see that the channel power for this pulse, when it is on, is about minus 6.38 dBm. This tells us the channel power of the signal while it's being transmitted, but does not tell us about the average power over time, taking into account the duty cycle. The traditional method for accounting for duty cycle to compute the average transmitted power over time is to convert the duty cycle value to dB and then use that as a correction factor on the measured channel power. In this case, the duty cycle is about 23.5%, which is about a 6.29 dB correction factor. However, there's an easier way. This can be measured directly. The analysis length can simply be extended to include the off time between the pulses, and we can fine-tune the analysis length so that it's an exact period of the pulse itself. And now we get a reading for the average channel power over time. To make this measurement even more accurate, we can encompass a larger number of cycles to ensure that we take into account any variation that might occur from burst to burst. In this case, over 15 or 20 or so pulses, we're seeing minus 12.76 dBm. Another advantage of measuring over multiple pulses is it tends to minimize the error that might occur if you don't make the analysis length an even multiple of the PRI, because now that error is going to be divided out over the number of cycles that you've measured. So by properly adjusting the analysis length, we can either measure the channel power of the transmitted burst itself or the average total transmitted power over time. The latter may help you to decide the heat sinking and power requirements for a given power amplifier, for example. Thanks again for watching.